Monday morning. It's the third time I've tried this. Okay, here we go for today. So last week we talked about the electromagnetic spectrum, and then we talked about the section of that spectrum which gives visible light. So those were your two lessons. Today the lesson is on colors you see associated with dyes and pigments. At the end of last week, I left you a couple options to test your knowledge. One was my own little Google quiz, and the other was the quiz from Gizmo. If you haven't done them yet, still try them to confirm that you're understanding what I'm talking about. There was one question on my own quiz about the kind of wavelength that penetrates the skin. There's actually two answers. I guess it wouldn't let you select both. If you picked one, you got the point. The idea was is you would pick both and got the point, but the way I set it up, it didn't work that way. So you should realize that both X-rays and gamma rays can penetrate the skin to be able to answer that correctly in a different situation. All right, so we're going to start with your note. After this, of course, I'll post some other things to follow up and make sure you understood what I talked about today. All right, so let's see if I can get this going. Yay! Exciting, yay. Okay, so here is the note for today. Let's start with the title, Subtractive Color Theory. See if this works. Yeah, subtractive color theory. Okay. So the main thing to keep in mind, just to briefly review where we were last week, the electromagnetic spectrum has all these different wavelengths. There's only one piece of that spectrum you can see, which is visible light, ranges from red to purple. Put them together, you get white light, which is the kind of light we have around us in our natural environment. That can be split back to all the colors in the rainbow. When you have a piece of glass or a raindrop in the sky after a storm, that will split the light and allow you to see all those different pieces in the full color range. Those of you that are artists will realize that if you're working with colors and paints and such, as you mix colors together, you don't get white, you get black. So this is an explanation, not of how light works when it, or sorry, not how when color works when it's in light. How color works when it's in light is the additive color theory we did last week. How color works when it's in dyes and pigments is subtractive color theory. All right, so the first thing we're going to write down here is that this theory applies to dyes / pigments. So when you think of like tie-dye or any kind of staining you do to fabrics, that's what you're doing here. So like if you are eating strawberries and that strawberry smushes on your clothes, it's probably going to dye your clothes, especially if it's white, that red color. So the strawberry itself had natural pigments in it that gave it that red color. And then when you put it on your fabric, it stained or dyed the fabric. So we use dyes and pigments from the natural world, from plants and berries and flowers, and sometimes animal species, like the mollusk we talked about that was the only source of purple for a long time. We take these molecules that occur in the natural world, or now we actually make them in a lab, and we apply them to paints and fabrics and things like that to make things the color we want them to be, whether it's our hoodies, like my nice red one here, or the color you put on your canoe, or whatever it might be. Okay, so the first thing we're going to write down then, we'll apply it today to artists, is that subtractive color theory is used by artists. In this situation, as you mix paints, you start with white and move towards black. Okay, and I'm gonna underline white and black. And so this is different than with color in light. Oh, I don't know if you can see that. With color in light, because in the absence of light, you have darkness or black. But then as you introduce colors of light, you move towards putting all the colors of light together and getting our natural white light as the culmination of the finishing product. If you work with paints or dyes, you know that if you start to squirt all these colors together, or Play-Doh or something like that, you may have handled at some point, mix different colors, you start to get darker and darker and darker until eventually you get to like a muddy black. So why is this happening? It has to do with the fact that the pigments that we talked about that are out there in the natural world that make leaves green or make berries red or make flowers blue are absorbing some wavelengths of the visible light spectrum and reflecting others. So if you absorb, it's going in, and if you reflect, it's bouncing back off. So just to give you a little idea here, let's talk about blue jeans for a second. Simple, easy to draw. If I have, all they're gonna look like, guys, nothing more elaborate, a pair of blue jeans. What is happening here is white light is shining onto this fabric, okay? And so for our purposes, we're gonna say that the white light is composed of three main pieces: the primary colors of light, which would be R means red, green, and blue, okay? What's happening is when that white light hits the dye that has been used to make these blue jeans, the colors that are absorbed are red and green. And what is reflected is only the blue. And that's why it looks blue to our eye. So here, red and green are absorbed, okay? And what bounces off of that dye or fabric is blue, okay? So blue light is reflected. And that's why the jeans appear blue. Oh, that's really, okay. Now it's maybe showing up for you. I have to work on my lighting in here. And that's what your eye picks up. Okay, so I'm gonna make a little chart here and we're gonna sort of work on this a little bit together. We'll do one more here. So let's say you have a little plant. These are supposed to be leaves. There's its pot, okay? Most of you know that leaves, unless it's the fall, are green. So it has to do with the pigment chlorophyll that would be in the leaf. And why the leaf looks green is because all the colors of light are absorbed except for green. So the plant actually makes no use of the piece of light that's green. If you tried to grow a plant in pure green light, it would die because it gets no energy from that particular wavelength. It's just reflecting it. It's not using it at all. It's actually absorbing from all the other pieces of the white light. And so, for example, you can grow plants really effectively in red light, but green light is actually useless to them. So there's a little aside. So once again, we shine the light on them, natural white light, which is a combination of red, green, and blue. And because this is a green plant, that means that the one thing that's reflected back to our eye is the green, and the pieces that would be absorbed would be the red and blue. Oops. Okay, green reflected, red and blue absorbed. All right, I'm gonna flip this over. I'm gonna make a chart. I'm going to do the first couple with you, and then I'm going to leave you to try and fill out the rest on your own. Okay, so here we're going to put color of object. Okay, and then we're going to put light absorbed. Sorry, this is messy. Oh, it's really not working nicely today. And then light reflected. No. Oh, maybe. Okay, so let's start with blue. Just did it, right? If the object looks blue, your hoodie, your car, whatever it is, that means that you're absorbing green and red, and it's the blue piece of the white light that's being reflected. If you have something that is magenta, this is one of the secondary colors you learned the other day. You kind of need to know what magenta is made of. So magenta is a combination of red and blue. So from white light, you'd have to reflect the red and blue parts for your eye to pick up magenta. Okay, that means the green is absorbed. If we do the same with another secondary color like cyan, okay, you have to figure out what are the two primary colors that make cyan. So what two primary colors are being reflected to your eye? And then the one that isn't used to make cyan is the one absorbed. So I'm going to let you work on that. And I'm going to put in here green and red. And let's just add one more, yellow. Okay. And then here's a thought for the end. What if it is black? And what if it is white? Okay. So I'm going to leave you with that. And then I'm going to come back to these and then the Google Meet tomorrow and discuss answers to this. I'll also post them at some point later so you can see. And then I'm going to ask some follow-up questions. Okay, so the learning goal we're working on right now has to do with understanding the conditions for reflection. I can turn this off for now, actually. There we go. Let's see. Where am I? Okay, so we're working on learning the difference between absorption and reflection and how that affects colors that we see produced naturally in pigments and what that means to how we dye our clothes and things like that. All right. So just keep in mind additive color theory is for light, subtractive color theory is for dyes and pigments. Finish that chart I gave you in your note, and then I'm going to attach some other pieces for you to work on. All right. All right. Take care, guys. I feel like today wasn't so smooth, but I guess it's like fake Monday. So that's bound to happen. All right. Talk to you later.